Your honesty hurts.
Okay, welcome to the IIBA Tampa Bay, Florida chapter study group for July 2022. This is our 46th consecutive class. Our goal here at the Tampa Bay IIBA Tampa Bay, Florida chapter group is to bridge the gap between industry leaders with business analysts by building partnerships with professionals, educators, employers, so that we may empower, instruct, and engage the IT community. You may notice that I've replaced our Florida picture with a map of the world because we do have people from all over the place joining us now. I've had people contact me and say, we've been watching your past study groups and it's helping everybody at work. And I'm like, yes, that's what we're here for. We have study groups every Tuesday night from 7 to 8 p.m. Eastern time. Our meetup address is here, Zoom, our past meeting recordings are here, our IIBA website, meetup and Facebook, as well as our LinkedIn groups. You have a lot of ways to reach us if you have any questions, and we're here to be of assistance. As I said, we have had a lot of classes so far. You can see classes 2 through 17. We're pretty much going through the BABOK. Since then, we've deviated a little bit. Currently, we're going through a guest speaker series. Last week, we had Damon Drake talk about being a developer and how BAs can best work with developers and what developers know that maybe we need to know. Today, we are probably going to have Bob Churchill talk about software from a different perspective. Bob has taught himself and learned quite a bit of software, as well as having several other things that he has learned. He's got letters after his name. It's pretty cool. As you know, we are a volunteer supported organization. Our board, you can see Cliff right down here at the bottom right in his X-Wing thing, right? Cliff, that's X-Wing, right? TIE Fighter. It's one of them. I don't know which.
It's the Millennium Falcon.
Millennium Falcon. See, I never know which side he's on. Sometimes he's on the dark side. He is our president. We have Lori as our vice president. We have board members at large. My name is Thea Raisins. I am the vice president of career and professional development. Tiffany occasionally joins us to help lead this study group. We do need more board members at large, board members that want to take on a specific role. Let us know if you're interested. We will put you to work only as much as you want to work. We want to use your skills to help the overall BA community get better. I mentioned Bob earlier. This is a fancy picture of him here beside his real picture of him. Bob is our resident CBAP. He's received his CBAP certification after taking his test through the IIBA. He also has, as I said, a bunch of other letters after his name. His website is very informative. I do encourage you to go look up things that you can't find anywhere else on his website. And we will turn it over to Bob to get started. Bob, I'll let you have the screen.
Can you see the screen?
We can, thank you.
All right. So I will tell you, I was totally not planning on speaking this evening, but I have this talk in the can. So that's a good thing. I'm gonna kind of bridge across from the subject last week that our guest spoke about. I learned how to program at Carnegie Mellon starting in the spring of 1981, I think. And as part of my mechanical engineering studies, I was a full-time programmer for about 15 years. I programmed in probably 20 different languages. They're all listed on my website. Maybe 6 or 7 of those things full-time. My favorite language is C++. That's what I probably did the most of. And I installed systems all over the world, and they're probably still running. By the way, Jordan Peterson had a talk with his brother-in-law, who is a chip designer, and gave a similar brief overview of what computers do and how software works. Their entire conversation is about 2 hours. So that's another take on this subject. He also talks about management and organizational behavior and getting people to work together and so on. Whoa, stop that. Let me share again. Okay, are we back?
Mhm.
All right.
Yes, they are.
I gotcha.
Hi, everybody.
Hello.
Glad to be back this week. I missed last week because I was on staycation. I took a break, but I'm back this week, so I'm glad to be back.
Okay, welcome.
Software does not like me to be running active JavaScript. Anyway, I did simulation for 30 years, both discrete event simulation and continuous simulation. Those are animated examples of both. I will make that go away, so maybe the screen will stop misbehaving. I've worked in a different pile of different industries. Almost everything I've done has really involved process analysis and engineering. So I tend to think of everything as a process and tend to take on challenges that are based on designing and improving processes and simulating them. The applications or design and sizing, so figuring out how big something has to be and how it works. Operations research, which is optimizing and understanding. Real-time control, simulation-based control systems simulate things you cannot measure, and then use the simulated values as the control variable to make things happen that you want to when you can't measure them directly. Operator training for nuclear power plants and other complex items. Risk analysis, economic analysis. Economic analysis you can perform by understanding A, the time value of money, and B, also assigning cost to every activity and every resource in a system. Impact analysis and process improvement. Some of the architectural considerations for simulation are continuous versus discrete event. Continuous is based on systems that are described by differential equations, and they're integrated over time. things like global weather simulations, simulations of the heating of steel, the flow of fluid over aircraft, that kind of thing. That's all continuous simulation. Discrete event simulation tend to be business processes and activities-based things where things take as much time as they take, rather than continuous simulation tend to march along at defined time steps. Interactive versus fire and forget. A training simulator will run in real time and it'll respond to your inputs like a video game. A fire and forget, you'll run something, you'll walk away from, and it'll run and complete as fast as it can. But once you start it, you can't affect it. Then real time versus non-real time, talked about that already. Single platform will run on one machine. Distributed simulations will run across many machines. If you think about a multiplayer video game, that'll be a distributed simulation of a sort. And then deterministic versus stochastic. That is a deterministic simulation. If you give them the same inputs, they always give you the same outputs. But with stochastic, you randomize certain things and run it a whole bunch of times to get a range of outputs, to see the range of possibilities that can result, and see what the typical outcomes are. So your KPI for something like that is something like this process will complete 80% of the time in less than 10 minutes. All the global health simulations that were done are stochastic, and they made a bloody mess out of every single one of them. Also, global weather simulations are mostly garbage. I could go on at length about all the errors in them. So that's me. That's not that important, but the first thing we need to know about computers is that they're really quite simple. They only really do about 6 things. And the first thing they have to do is be able to store information. And they can store information as numbers of various sizes that are capable of storing different ranges of values. And they will take up different amounts of memory to do so. And then once you have the basic types, and sometimes there will be letters, sometimes there'll be numbers, sometimes there'll be colors. When you combine them into strings and records and arrays and structures and objects, then you have can represent any kind of more complex entity or process. And then depending on how the languages work, those memory locations will be packed in different ways. So you have to know a lot about what's going on inside the computer to know how a given language is handling all this. USBAs don't need to know about this stuff. And increasingly, most programmers don't even know about a lot of stuff because computing is now so cheap that a lot of things have been simplified and abstracted to make the programmer's life easier. But the best programmers will all know all this stuff down to a pretty low level. The more you know about it, the more you'll be able to talk to programmers about it. So that's why we're doing this brief introduction for you. So like I said, computers can only do a handful of things. They can do I/O or move data around, right? Move data from one place to another, and that means move data from outside the computer to the inside. Move places, move information from one area of memory to another, and sometimes it's in the long stream of external memory, and sometimes it's within the actual CPU. And then you'll put information out in terms of pictures, sound, recorded stuff, a lot of different forms of physical actions, for example, CNC controlled manufacturing machinery, and so on. So basically, all that is forms of moving information from one place to another. You can add two numbers. So subtracting means just kind of inverting one number and then adding the two numbers. And then you can do bit twiddling. So that means shifting all the bits one step one way or the other, masking them, inverting them, doing logical operations, and so on. So if you want to know how a multiplication works, in reality, it is just a series of adds and shifts. So, and division is the opposite. It's subtractions and shifts down. And it gets way more complicated than that. But in reality, that's all computers do. And then there are some meta operations that they do. You list all the instructions in memory, and you execute the first one, then you do the next, then you do the next. Except when you jump someplace else other than the next instruction. And then you can stop executing. In reality, that's all any computer is doing, and everything that they do is at an abstract buildup of those very simple operations. And it takes a team of people that know how the physical hardware works and how the atoms in semiconductors work, and how CPUs and memory and electrical engineering and communications are happening to get all the way up to something we can use.
So Bob, I'd like to ask you a question. BAs wouldn't normally create their own simulations. They would rely on a developer or a programmer to create a simulation, correct?
Well, yeah. So, I mean, a BA generally wouldn't create a simulation or software at all. There is something going on now, a big move called citizen development, and that is simplifying and abstracting the process of making computers do what you want so simple and so abstract that almost anyone can do it. You still have to be smart, but they're taking away a lot of the hard parts and hidden them from you so that many more people can do development-like things. If you imagine building a house of Lego, if I gave any of you a box of Lego, you could build something that looks like a house. And that's on kind of high level programming, right? Or very abstract. But if I told you you had to make all the Lego bricks by distilling petroleum products and doing injection molding and getting the colors and temperatures right, and making the actual bricks themselves, that'd be a way more involved and complicated process. And that's kind of what programming has become over about 60 or 70 years. It's gotten increasingly easier and more abstract, but you know, it's still not there, and you can still get in trouble.
I love
Well-
our no code, first code solutions. No
Yeah.
code is a long way from happening, in all honesty.
Yeah,
Yeah.
Everybody tries to push their version of, oh, low code, no code, but yeah, they're not there yet.
It's one of those things like self-driving cars. In most cases they can do it, but those edge cases where they can will kill people and cost a lot of money. And you know, some things are very complex. I've been doing this for over 40 years and I don't do it much anymore from day to day, but I still learn things. So it's like anything, you can always learn more and get better. So let's talk about how computers operate at various levels. There's the BIOS level, which is how the machine starts up and does its most basic things. Then there's the operating system, manages, processes, provides background services, and facilitates access to all the hardware on your machine. All the drivers and so on. They make the sound work, the keyboard work, the disks work, the screen work, the speakers, cameras, all that. Applications are the things that do what users want. So word processors, art programs, graphics, Visio, Excel, numerical calculator, simulation, those are all applications. And then you have cluster type levels. Amazon might have 20,000 actual servers all doing the same thing over and over for 20,000 people at a time. So they'll all work together, they'll work independently, they have to be coordinated, there's an overhead to all that. And there is a level of expertise required for operating at all those levels. So unless someone is a total genius, and basically none of those exist, no one can really operate effectively at all those levels. It takes a team of people working together to make it happen. So programming tools exist at various levels of abstraction. What they ultimately attempt to do is take something humans can think about and do the busy, difficult, detailed work of turning that into something the machine can understand. And that can happen in 2 or 3 passes. Things can be interpreted, which is processed on the fly. They can be compiled so it reads everything once and prepares the machine code. But you need a layer to go between what you write in the computer, because we tend not to think about things the same way a computer does. In a lot of cases, we automate the writing of code. Compilers, for example, will fold a lot of automation into your code and whatever your source code is. And the more abstract and modern the language, the more it's doing stuff behind the scenes. If you have a graphical programming language where you're moving boxes and connections around, it'll write all the code from that in the background to make the computer do what you want. The tools help you not screw up. So if you do a low-level language like C++, you have to do everything yourself. You have to manage memory. It'll do something for you. But you always have to test, see, for example, that you weren't running out of memory, that you're not overwriting memory. So a lot of modern languages have taken what we learned over the years and they keep you from doing anything stupid, but they impose a lot of overhead in terms of duty cycle and how hard the CPU has to work in the background. So you're trading one kind of efficiency for another, and we'll revisit that again. We'll integrate reference material. That's always interesting. That can be in the form of help and other helpful things to make sure you're doing the right thing. You'll integrate debugging and test operations. So when you're writing code before it ever leaves the developer, there's a lot they can do to make sure it's going to work correctly. At least at first, they have control over things. You can't always do integration testing and cover everything having to do with timing, which can be very complex, but at least you can really ensure a lot of code quality right at the source. I did that for years. a lot of what we do, the problems in computing haven't really changed since the whole enterprise started. But what we're doing is managing larger and more complex projects. And that's really a lot of modern practice is about managing complexity. We want to enhance and organize collaboration. That means if we're doing large, complex processes, we have the BAs as the go-betweens between the customer and the technical team. That's one form of collaboration. But there are also many levels of specialists at different levels of complexity in the hierarchical computing stack. And there are people that have parallel specialties also. And you have to make all of them work together. And all these tools help make that happen. GitHub is one example of that. There are other program analysis and sharing and management tools. Managing complexity, I've talked about that quite a lot. So there are only a few main language constructs. I told you before, computers only really do 6 things, but at the next level, IO is reading stuff in and out and writing. There are math operators, string operations having to do with text and language, creating and deleting entries as in a database. So new customers, information about orders, account numbers, transactions, all that. If then else conditional. So a lot of times you, depending on the incoming value, you'll do one thing or you'll do something else. For example, can a person own a bank account by themselves? Well, yeah, if they're 21, but maybe if they're between 18 and 21, they have to have a cosigner that's at least 21 and under 18. They have to have some kind of a custodian account. So there are a lot of places where these conditional come up, and case and switch statements are just fancy forms of chain if then else's. Then you have counting loops, which is do this X number of times no matter what. You have a test at the top loop, which means you're going to do the test and then you may or may not execute the code, but you'll execute it as long as the condition is true. And then there's a test at the bottom loop, which is almost exactly the same, except that you're guaranteed to run the code within the loop at least once. And really all these are is a form of doing some stuff to mean if then and either executing the next instruction, which is the default, or jumping someplace else to execute a different instruction. That's all those are. So again, these are made up of very simple operations. Jumps go to the same thing. Subroutines are jumping out to another series of code. saving the state, doing something repetitive, and then coming back probably with a result or a side effect. So all the different languages group those operations together. They aren't really part of languages, but all languages do that. If you look at the vast majority of languages, there are about 30 basic constructs in every one. And then everyone does a few specialized things. But mostly they all do the same things, and there's a reason that all these different languages exist. They're all trying to make certain things easier or more clear or give you more power. Now, the libraries and application frameworks are often the most difficult part of learning any language. The language might be this big, but the APIs will be this big. I mean, they'll be absolutely huge, and it's piles and piles and piles of code to do fairly standard things. In my favorite language, C++, there has long been something called the STL, or Standard Template Library. If you are into JavaScript, there are tons of libraries and frameworks, and learning JavaScript itself isn't that hard, but learning all the libraries, especially as people create new ones seemingly every week, that can be a bit of a treadmill. I won't go into this in detail. Excuse me. All this is on Wikipedia. There are a ton of different kind of computer languages. They all do different things. They all specialize in things. In reality, they're all built on the same small elements. But if you drive down the street and look at all the different types and shapes of houses, and look at houses that are built by primitive peoples in jungles or on the plains in Africa or wherever, or if you build a house on the moon, they're all going to look very different. They'll have some things in common, but they'll all use different materials and have different design elements. So languages come in every kind of variety you can imagine. So there are generations of languages. The early stuff was written at a really low level. And that was starting in the 1940s. And you basically flip switches to talk to the computer directly in terms of ones and zeros. And then almost immediately, people came up with a slightly higher level way of doing that, called assembly language. It's a little more human readable, but it's still very low level, and you have to learn how to think very differently as a person to be able to program this way. In the 1950s, we started to see high-level languages, and still most of the way programming is done is probably mostly still at this level. Then we have fourth generation languages get more complex, more high level, more specialized. But really most of the work still at level 3. And then in theory, people have been trying to create 5th level languages, which are even more automated and abstracted, in theory simpler, but they really haven't gotten anywhere. I mean, it's kind of an unfulfilled promise. It's like it's essentially a complex process, and you really need to understand it in order to be able to do it. So have a little respect for your programmers, even the worst ones know many things you don't. And as a programmer and analyst, I had to learn both sides. And really the advent of pure analyst and BAs and go between customers and programmers, that's really a comparatively recent development. When I was starting, I was the one who taught directly to the customers, did all the analysis, figured out all the requirements, and then I wrote all the code. So one person had to be able to do kind of everything. And then there is a word, people have been joking about the word paradigm for as long as I've been in the industry. That link goes to a Wikipedia article, just like there are many kinds of programming languages that do different things. They're done different paradigms. So let's talk about trade-offs. We have all these different languages and paradigms, and why do all these things exist? So let me ask you a question. Is it more important to optimize software on speed or memory? Flip.
Honestly, speed wins every time.
Yes
me.
and no.
In
Okay.
today's computers, memory is almost unlimited. So, and stuff can be chained together for speed. So usually speed is the most important.
Why don't we program in assembly language then? That'd
Because
be
nobody knows that anymore. Nobody knows that. No, yeah.
The answer is it depends. So speed is important. Cliff is absolutely right, but speed of what? Is it execution speed or development speed or the speed of getting something that'll run halfway decent in the hands of a customer who can use it and immediately start realizing benefits from it? That's really the kind of speed we're talking about in the long run. Okay, so with power comes responsibility. If you're going to do things close to the metal, right, close to the hardware, you have to know enough not to make mistakes. But a lot of modern tools prevent you from making mistakes, but they also prevent you from doing a lot of tricky and clever stuff too. And the benefits of this are You reduce errors, improve productivity and collaboration, and you can manage more complex stuff. And the cost, or it takes more computing power, but as Cliff correctly points out, if computer power is cheap, who cares how much you use? The ability of people to get stuff done and the intelligence to meet people's needs, customers' needs, that's what you're actually making use of. So you're burning computer power, you're taking control out of the hands of programmers, and a lot of programmers no longer know what's going on under the hood. Now, many of them often don't need to in any case, or in every case, to be effective. But somebody still needs to know all the details. So that's why we have a division of labor, right? So some examples are, excuse me, automated memory management. It used to be you'd have to keep a close eye on memory, but now the languages do that for you. They won't let you do it. But that imposes a lot of overhead in the background, and it really makes you go through a lot of extra steps, and there are shortcuts you cannot take. It used to be that you'd have very specific data types for different kinds of data. So if you remember that first page, there were like 15 different definitions of numbers. Many modern languages give you one. Every number looks the same, and that's all you get. But it's simpler and faster, but it's wasteful in a sense. Interpreting versus compile. So that's a different trade-off. Reduce low-level control. It used to be you could represent groups of numbers and individual numbers in multiple ways by referencing memory definitions that were overlaid on each other in memory. But many modern languages will not let you do that anymore. And I find that annoying. I want to do that a lot, and I'm not allowed to. So that's annoying. So
That's why operatings exist, Bob, to stop you from doing that.
well, yeah. But I'm old, you know, who likes change? So here are things that we talk about trade-offs. There are all the areas within computing in people and methods and costs, right? So computing, we have execution speed, response time, memory, disk, clarity, modularity, and a whole bunch of other things. And those are all trade-offs, right, with each other. And then we have the needs of people and methods we have to consider. And they're often at cross purposes, but you kind of need everyone's input to succeed. In the more complex of a system you're trying to put together, the more those people are going to be involved. And then costs come from many different sources: software, hardware, licensing, maintenance, upgrades, fixed versus variable, installed versus maintenance. So you always have to balance everything. The ultimate optimization. So I've studied economics literally almost daily for over 20 years now. And in reality, one of the functions of money is to serve as a unit of account. And that allows organizations to calculate profit and loss and figure out how to compare and judge the effective usage of all different kinds of resources. So ultimately, you're trying to optimize to minimize the total cost of ownership over the entire life cycle of a problem or solution. So let's talk about something near and dear to our hearts as BAs. What we're trying to do is team up with the programmers to solve customer problems. We're the go-between, and we have to. And let's say we're the speaker or listener, whether it's a customer or some kind of a technical person, we have to go through all these steps to make sure we communicate clearly. So it goes through what we think we said, what we actually said, the information that actually got transmitted, what the listener actually heard, and how he or she interpreted what they actually heard. So there are a lot of barriers to doing that well. These can be mitigated by error checking mechanisms and by being clear in the first place. But basically, the more you know, and the more of a rapport and expertise you share, along with patience and empathy, the better communication will be. So that's why all my processes, for those of you who are familiar with my framework, they're iterative. So when you're iterating within a phase and between phases, you do that, check your communication. That's really what it's all about. So computers talk to each other, and the internal parts of computers talk to each other. I wrote a bunch of articles on this. I won't bother you with it now, but it's a complex subject. And whether you're talking to microservices or talking to a server over the internet or interacting with your phone, all those devices and systems are doing this inter-process communication and verification and tagging and unpacking and interpreting, and there's a lot going on. So you have to be careful. You can't assume they'll just work. If you do that, that's a one-way ticket to Beluga Mill. there are a lot of things you have to think about. You might want to log every single thing that happens so you can figure out what went wrong when things do. You have to be aware of data types and formats. So one thing we used to do in low-level languages is have many different data types. But with the internet, you have all these different kind of computers talking to each other. And what they've chosen to do is write everything out in a kind of verbose text, which is very consistent. So we've done a trade-off is we are sending a lot more information, but we're making a lot fewer mistakes. And there are many different kinds of information that we can send: video, audio, images, specialized document formats, and so on, that are as many and various as you can imagine. So that is the way I think about working through processes, no matter who you're talking to. Everything is always improved by knowing what they're doing and them knowing what you're doing and trying to accomplish, along with patience and empathy. I cannot stress enough about patience and empathy. Many of you who are natural BAs are probably naturally good at that. As a techie geek nerd who kind of became a happy-go-lucky, peace-loving super communicator, cough, cough, hack, hack, I've had to get way better at the patience and empathy. On the other hand, you know, nobody appreciates it more than me, because it's something I've personally struggled with. So all the documentation, review, and feedback and correction are human forms of queuing and retrying, and that's what all the iteration is. This diagram is all about iteration. Non-functional requirements, those are qualities that the solution should have. There's a list of about 60 possible examples on Wikipedia. You might go check that out. You can find this presentation on my website under on the portfolio page under presentation. It's like number 5, it's software. So feel free to check this out. Click on any of the links I provide. Hopefully a friend of mine will talk about UI UX. That's one aspect of how you talk with computers, and there are many different aspects of that. They want to make it easier to display and understand information and give you control over what the computer is doing, and also help you ensure you know what state you're in. That's always very important. And good UI, if it does all those things, will keep you from making mistakes. And then if you do make a mistake, or if the computer does, you've got the best possible chance of recovering from it. And I won't go into that in too much detail. Again, I've asked a friend of mine who's an expert in UI UX, who I have the highest respect for. Hopefully she'll be able to address you sometime within the next month. So what are the overall trends? Basically things are getting more abstract and simpler, and it's all in service of getting work out to the customers quickly and more accurately. At the end of the day, the problems in commuting are the same as they've always been. Nothing has really changed. Changes or incremental things are getting better slowly, one step at a time. There's never going to be a silver bullet or a final answer. And with that, we'll live, by golly. Thank you for listening. Do you have any questions?
Okay, with that, I'm going to take over the screen for just a minute. Next week, we'll have Keith Nolan talking with us. He is a business architecture and process leader at Disney Cruise Lines. And he's going to talk about how they determine what projects that they bring forward to the folks to work on. And that will be a week from now. We have Tammy Bearden coming back. Hopefully the UX UI expert that Bob talked about will be coming back. I'd like to get a project manager in here. If anyone has a project manager who'd like to speak about working with BAs and what their responsibilities are. And then we're going to go back into the CBAP questions, beginning with the introduction in chapter 1. So if y'all can help me find a PM, I would appreciate it. I will be announcing the week after next guest after Keith next week. Okay, guys, thank you very much. Bob, you did a fantastic job as always.
Let me get the link to the slides in the chat before we go.
Okay, drop it in the chat.
And Daniel, if you reach out to us, we do store these recordings and make them available.
Awesome, thank you.
If
Are
anyone,
you in our LinkedIn chat? Sorry, are you in our LinkedIn channels and Meetup or anything like that?
Not yet. I had just sent a request.
Okay.
if anyone needs any mentoring, reach out to me through LinkedIn. If anyone is looking for a position or has a position to fill, let me know and I'll try to do the matchmaker thing. I just got informed that my contract is coming to an end, so I'm going to be one of those people looking for a position. So let me know, guys. I will talk to you all next week. Thank you very much.
Thank you.
Thank
you. Thanks, Bob.
Guys, have a
Bye.
wonderful week.
Bob.
Thank you. Have a good evening.
Bye-bye.